Black holes eat stars. They swallow planets. Even light cannot escape once it crosses the edge. So you might think a black hole lives forever, but it does not. One day, after an almost impossible amount of time, a black hole may begin to disappear, and its death becomes stranger every second. It does not get old. It does not become sick. It does not simply shut down. Instead, it slowly leaks energy. It shrinks. It becomes hotter. Then it leaks even faster. It is like an ice cube that heats up as it melts, which makes no sense. At least not yet. For most of its life, the black hole loses almost nothing. Then the process speeds up. Slowly at first, then quickly, then incredibly quickly. And during its final moment, physics itself may stop giving us clear answers. So what actually happens when a black hole dies? Let us start at the edge. A black hole is not a giant space vacuum cleaner. From far away, its gravity works like the gravity of anything else with the same mass. If you watched our last video, you'll understand what I'm about to say. Replace our sun with a black hole of equal mass, and Earth would not suddenly fall into it. Earth would continue orbiting. We would freeze, but we would not be sucked away. The real danger begins only when you get too close. Around every black hole is an invisible border called the event horizon. Think of it as the edge of a cosmic waterfall. Far from the edge, your boat can still turn around. Closer to the edge, the current becomes stronger. Cross the final line, and every possible path carries you deeper inside. The event horizon is not a solid surface. You would not crash into it. There is no wall, no door, no warning sign. For a very large black hole, you might cross the horizon without immediately noticing anything unusual. But after crossing it, returning to the outside universe becomes impossible. But if nothing escapes, how can a black hole lose energy? For a long time, scientists thought it could not. A black hole could eat, it could grow, it could crash into another black hole, but it could never become smaller. Then physicist Stephen Hawking mixed two very different rule books. Einstein's rules for gravity and quantum physics, the rules of extremely tiny things. The result was shocking. Black holes should not be completely black. Quantum effects near the event horizon should produce a tiny amount of thermal radiation. Today, we call it Hawking radiation. The black hole is not throwing out material that was trapped inside. Nothing is climbing back across the horizon. The effect happens because quantum fields behave strangely around that horizon, and this tiny glow carries away something important: energy. When radiation escapes, it carries away energy, and because mass is a form of energy, the black hole loses a tiny amount of mass. Imagine a piggy bank with a microscopic hole. One coin falls out every absurdly long period. At first, the missing coins barely matter, but given enough time, even the biggest piggy bank can become empty. You may have seen Hawking radiation explained using two particles appearing near the horizon. One escapes, the other falls in. That picture is useful as a cartoon, but it is not the complete physical explanation. The real mathematics involves quantum fields across curved space, which is much harder to draw using two smiling dots. Luckily, the result is easier to understand than the mathematics. A black hole has a temperature. It releases radiation. It loses mass. And if nothing replaces that lost energy, it can eventually evaporate. But there is one problem. The black holes in our universe are currently surrounded by light, gas, dust, and background radiation. They are still receiving food, and most are far too cold to die. Space looks cold, but it is not perfectly cold. The universe is filled with faint background radiation left from its hot beginning. Large black holes are even colder than this background. So today, they may absorb more energy than they lose through Hawking radiation. It is difficult to lose weight while the universe keeps delivering snacks. For the black hole to truly begin dying, the universe must change first. Stars must stop forming. Existing stars must burn out. Loose gas must become rare. The universe must expand, cool, and grow darker. Eventually, a lonely black hole may have almost nothing left to eat. No nearby stars, no warm clouds, no steady stream of matter.
only an enormous, quiet universe. Now the balance changes. The black hole still emits its tiny Hawking glow, but almost nothing falls in to replace the lost energy. The cosmic piggy bank starts emptying very slowly. You could wait trillions of years and barely notice a difference. And the larger the black hole is, the longer the wait becomes. Here is the strange rule. Big black holes are colder. Small black holes are hotter. Imagine two cups. The giant cup contains ice-cold water. The tiny cup boils. That is nearly the opposite of what your everyday instincts expect. But for black holes, temperature rises as mass falls. A black hole with the mass of our sun would have an incredibly tiny temperature, far less than 1 degree above absolute zero. A supermassive black hole would be even colder.
So its radiation would be extremely weak. It would spend nearly all its existence doing what appears to be absolutely nothing. But the clock is still moving. A black hole with roughly the sun's mass could survive for around 10 to the power of 67 years under standard estimates. That is a 1 followed by 67 zeros. Our universe is only about 13.8 billion years old. Compared with the black hole's lifetime, the universe today is barely a newborn. Supermassive black holes last even longer. Their lives stretch across numbers so large that they stop feeling like time. Galaxies can fade. Stars can disappear, planets can freeze, and the black hole may still have almost all its mass. But eventually, even that giant begins to shrink. Then the slowest countdown in history begins to accelerate. When the black hole loses mass, it becomes smaller. When it becomes smaller, it becomes hotter. When it becomes hotter, it emits more radiation. When it emits more radiation, it loses mass faster. And when it loses mass faster, it becomes even hotter. The process feeds itself. Imagine a snowball rolling downhill, except instead of becoming larger, it becomes smaller. And the smaller it becomes, the steeper the hill gets. For most of the journey, it barely moves. Near the bottom, it races. Black hole evaporation follows a similar pattern. Almost the entire lifetime is spent in the slow part. The black hole has entered a runaway process. As its temperature rises, the black hole can release more energetic forms of radiation. At lower temperatures, only very light particles can be emitted efficiently. As it grows hotter, more types of particles become possible. The quiet object begins changing into an increasingly energetic particle machine. But do not imagine a large stellar black hole suddenly exploding tomorrow. That is not how this works. The black holes created by dead stars are far too massive. Their evaporation times are fantastically longer than the current age of the universe. The possible exceptions would be much smaller hypothetical black holes created in the early universe, and some of those tiny black holes could already be near the end. Scientists call them primordial black holes. They may have formed from extremely dense regions shortly after the universe began. But we do not yet have definitive proof that they exist. But if a primordial black hole formed with the right small mass, its lifetime could be ending around the present cosmic era. Finding one would be extraordinary. It could provide evidence for Hawking radiation. It could reveal information about the early universe. And it might show us particles and energies that are difficult to create anywhere else. But detecting the final signal would not be simple. Space produces many bright flashes. We would need to identify the correct one. Now imagine that we can safely watch an evaporating black hole. It has already survived almost its entire lifetime. Its mass is falling. Its temperature is rising. Its radiation is growing stronger. The black hole that once spent ages whispering into the universe is finally beginning to shout. But the final shout may not look the way movies show it. A black hole does not contain a giant bomb waiting to explode. Its final energy comes from the mass it still has. As evaporation accelerates, that remaining mass is converted into outgoing radiation and particles. The black hole becomes smaller, hotter, and brighter. Its event horizon contracts toward an unbelievably tiny size. In simple models, the last stage may produce a rapid burst of high-energy radiation, possibly including gamma rays and many types of particles. But saying exactly what happens at the final instant would be dishonest.
Our current equations work well while the black hole is still much larger than the smallest scales in physics. Near the very end, that safety disappears. The last page of the instruction manual is missing. Gravity is normally described by general relativity. Tiny particles are described by quantum physics. Both theories are extremely successful. But during the final stage of black hole evaporation, we may need both at once. We need a complete theory of quantum gravity, and scientists do not yet have one that has been experimentally confirmed. Maybe the black hole disappears completely. Maybe it leaves behind an incredibly tiny remnant. Maybe the final evaporation behaves differently from the simple calculation. Several ideas exist. None has been confirmed by watching a real black hole complete the process. The honest ending is not a clean answer. It is a question mark. And the biggest mystery is not what happens to the black hole, it is what happens to everything the black hole swallowed. Imagine throwing a diary into a fire. The diary is destroyed, but in principle, the smoke, heat, and ashes still depend on what was burned. The information becomes scrambled. It is extremely difficult to recover, but physics expects it not to simply vanish. Now throw the diary into a black hole. The black hole later evaporates as nearly thermal radiation. If that radiation carries no trace of what entered, the information appears to be destroyed. This clashes with an important rule of quantum physics. This problem is called the black hole information paradox. Solving this puzzle could change how we understand reality. Some modern ideas suggest the information may be hidden in extremely delicate patterns inside the radiation, like shredding a picture into trillions of pieces and scattering them across space. The picture still exists in principle, but rebuilding it would be almost unimaginably difficult. Other proposals describe remnants, altered horizons, or deeper structures in spacetime. Scientists have made major progress, but there is still debate about how the full answer works in our universe. That is why the death of a black hole matters. It connects gravity, heat, time, quantum physics, and information. A tiny dying black hole could test some of the deepest ideas humans have ever created. So does the black hole truly die? According to the standard Hawking picture, yes. It loses energy, its horizon shrinks, its temperature rises. The process accelerates, and eventually the black hole reaches a final quantum stage. But the precise ending remains hidden behind physics we have not fully discovered. A black hole's death is not one sudden event. It is a story told across almost unimaginable time. But perhaps that missing answer is the most important part. Black holes teach us that even the darkest objects may have a temperature. Even the strongest cosmic prisons may slowly lose energy. And even something that appears eternal may only be living on a clock too large for us to see. The universe is patient, very patient.